All right, in this video's lesson, we're going to be talking all about some of the ways that graphs can be misleading. Um, and this is really an important section. In fact, it's one of the most important sections because not only is it important to know how to make a graph, but also to be able to identify when a graph is not telling the whole story. Because a lot of times, especially with advertisements and things that are posted in the media, graphs that are used are not the best. In fact, a lot of them are made to make you think a certain way when really the actual data behind the graph is telling a totally different story. So this is probably one of the most important sections for us to talk about in this second unit. So when is it inappropriate to use a pie chart? Well, anytime that you have parts that are not of a whole, that's going to be a problem. In fact, I think that's something that we talked about in the previous video's lesson, was this idea that you have to have parts of a whole in order for a pie chart to be appropriate. And obviously, we also talked about how pie charts are not the best for comparisons as well, which is another thing to think about as you're deciding between kind of a pie chart versus a bar graph. So I've got this kind of funny cartoon for you, and I'll just kind of read it to you. It says, "I didn't have anything useful to say, so I made this pie chart." And everyone's real impressed. Ooh, it must be true because it's pie. And he's like, well, that worked way too well. And they're over here pledging their life to the pie. And so, yeah, I mean, the pie chart really is not, in terms of a statistical value, it's not worth a whole lot. So we tend to use bar graphs more oftentimes than not. So that's going to be what we'll mostly focus on for the rest of this section of the notes. So what are some common ways that a graph can be misleading? Well, the first thing is that the labels are missing. So yeah, obviously if the labels are missing, that's going to be a big problem because now your graph, you don't even know what it represents and you don't know for comparison kind of what's going on. Lots that can go wrong there. Along with that is this idea of what's called truncating. So truncating a graph is when you take, especially in a bar graph, if the bars are going to be kind of really high, you truncate and you make them shorter. So you kind of cut out a section of the graph. So rather than starting at 0, you started at a higher number so that you don't have to draw the bars up quite as high, which at first sounds like a good idea, but the problem then is that the comparison is going to be off. And we'll see an example of this in just a little bit. The last is anything that violates the area principle, which for your convenience, I've got the area principle kind of written for you right over here, which is that the area occupied by a part of the graph should correspond to the magnitude of the value it represents. In other words, it should look kind of the same as the number that's being created from. And so some problems with that you can lead to from the area principle, a lot of times 3D images are going to be a problem. Because 3D images will then deal in terms of volume rather than an area, and a lot of times that's going to make the comparison not accurate. Also, you have to be careful with the widths of the interval. Typically the heights you don't have to be as careful with, but the width of the interval can definitely make a big difference when you're thinking about the area principle. So let's use some of that information to talk about what's wrong with this graph with DirecTV. Now, obviously, again, meant to be an advertisement. They were probably not intending it for it to be used as an actual graph, but it'll give us some good things to talk about. So you've got DirecTV stomps the competition. DirecTV apparently has 95 of your favorite HD channels, and they've got those listed. Then you've got Dish Network at 81, but not really because they count 24 of their part-time channels. And then cable at 56, but again, only in a few major cities that they have that many. So let's talk about kind of what's wrong. Probably the first thing to notice is the widths of the intervals. It definitely violates the area principle. So again, those widths at the bottom really need to be the same if you're going to accurately compare the number of channels for each network. In addition, take a look at the heights. I mean, if you're looking at, if this is a height of 95, 81 it looks like is almost half of that. And that's only a difference of 14. Whereas looking at the height of dish network versus the height of cable, you've got a very small difference, and that's a difference of 25. So not even the heights are kind of incorrect as well. I'm just going to say that the heights are not proportional. And then obviously you've got some other biases that are skewing the data. So I'm just going to write biases here where they're talking about, especially the wording bias, that obviously they are trying to sell you on something. And so they're trying to make their graph look as though it's trying to be sold for DirecTV. So obviously they were not intending for this to be an unbiased graph by any means. All right, let's take a look at another example. So we've got this graph where we're told what the numbers of buyers were compared to their previous computer. So first thing that jumps off the bat to me is that these 3D images are going to cause some problems. A major problem is you really don't even know what the height of these are. For example, let's take a look at the Macintosh. Are we going to say that the height is based off of this point, which is around maybe 350? Or are we going to say it's based off of this point, which is probably closer to 310? So you've got kind of two different heights that you don't even know which one's which. It also, once again, violates the area principle just in that 3D images by themselves are going to violate that, but that also means that the widths are going to obviously be different for each of those. So that's going to be a problem as well. Obviously, you've got some biases here as well. If you take a look at the type of computer that's being shown, and pretty much all of them, the image looks like it's that of a Macintosh computer or a Mac. And so obviously, once again, probably a graph that was created to induce some of those biases, hopefully was not meant to be used as an actual graph. Okay, so in an attempt to fix that, here are two different bar graphs that show that same data as what was on the previous page. So these are coming from this diagram right here. And so we want to know which one would be considered deceptive and why. And so taking a look at them, maybe at the first glance, you might not even notice kind of what the difference is. They both have the labels, they both have bars now instead of the images. They both go up to 80. But then the big difference is they both don't start at 0. The graph on the right actually starts at 10. So in the graph on the right, this is an example of a truncated graph. So you're not starting at 0. And so you can see why that's going to be a little bit deceptive. If you're not careful by looking at the labels, you look at PC and it looks almost as if PC is at 0, whereas on the graph on the left, pretty clearly PC is above 10. It also makes it look like none is much higher than PC, whereas on the other graph, you can see that the difference in heights is not quite as noticeable. So which one would be considered deceptive? Definitely this graph on the right would be your deceptive graph. And as for the explanation and the reason why, it's because it's been truncated. All right. One more graph to look at, and that will be it for this video. To give you a little bit of background on this graph, this was actually a graph that was used in a training that the Shawnee Mission School District did I think, second year of teaching. So it was at the in-service right at the beginning of the school year before we went back. And it was in a session where the presenters were talking about the differences in the learning styles of girls versus boys, which I thought was going to be pretty interesting. And so throughout the course of it, we're learning different things. And then they used this graph to talk about the mean IQ level between girls and boys and how those compare at different age levels. And so as soon as I looked at this graph, I was like, I need that graph. So I took a screenshot of it. Now, the reason I needed it was not because it was a real great graph, but actually because it was a not so great graph. So let's talk about why this graph is maybe not so good. To start off with, obviously you're using pictures. And anytime you're using pictures, that can be deceptive. Now, the area principle is not violated. However, when you're looking at girls versus boys at age 7, notice that at age 7, girls, it looks like, are pretty far ahead of boys. There's this kind of gap between the two, that girls are much higher. Whereas at age 11, that gap becomes shorter. And then at age 16, that gap actually flips around. And now at age 16, you've got that boys are actually ahead of girls in terms of IQ. But what you want to really kind of think about too is, let's just think about the differences in the IQ level at each of those points. At age 7, the difference is only 1.2. So girls are 1.2 IQ points ahead of boys. And at age 11, the difference is even smaller, 0.8. And at age 16, the difference gets switched around, so boys are now ahead, and it looks like they're ahead by 1.6. So these are some pretty small differences in terms of numbers versus the pictures that are being shown, which can definitely be misleading because, again, when you look at a graph like this, your eyes are probably drawn to the pictures more so than they are to the numbers, at least at first. The other thing is that the bars are almost unrecognizable. In fact, until I said something about the bars, you maybe didn't even notice that on the right side here of this, it is in fact a bar chart, and they are in fact comparing those using bars. And once you notice that, it probably becomes even more apparent that, wow, there is really not that big of a difference between these. The bars even indicate that. So definitely not a good graph if you're trying to, from a mathematical or a statistical standpoint, show that these two IQ levels are different as the ages change. All right, so what we're going to do, this is actually going to lead into a short kind of mini project that we're going to do for this unit, where you're going to go out on your own to find some graphs that are misleading, talk about why they are misleading, and then provide a new graph, kind of like what was done up here, that will hopefully help you or help other people to see it in a little bit better light. That being said, that's all I've got for you. Until next time, have a good rest of your day.